In this video, we're going to look at misuses of statistics. And one thing I want you to recognize is that statistics is very powerful. It can be used to predict and make generalizations about a population. It can be used to describe a population, but when it's not used properly, it can be used to manipulate information to businesses or individuals or advertising firms' own advantage. And so when you look at statistics, you need to be able to look at it with a critical eye so that you know when you have information that might be biased or inaccurate to try and sway you to believe one thing versus another. There are essentially two questions you should ask yourself when you see a statistic. You should first ask yourself, was the sample used to gather the statistical data unbiased and of sufficient size, meaning did they ask enough people? Or clusters if it was cluster sampling. And then the second question should be, is the statistical statement ambiguous? That is, can it be interpreted in more than one way? In the book, they provide two examples where you might see bias. One example is an advertisement where they say 4 out of 5 dentists recommend sugarless gum for their patients who chew gum. And you have to think about it. We don't know the sample size. We don't know how many times the experiment was performed to obtain these desired results. Maybe they asked 50 dentists one time and like, do you recommend sugarless gum to your patients who choose gum? And out of 50, only 3 of them said yes. What if there were 1 out of 100 dentists don't recommend you chew gum at all? That information is missing and misleading about these statistics. Another one might be the other example in the book is from a golf ball company. They say that the driver golf ball gets hit and goes further than any other brand of golf balls hit for the same number or hit in the same manner the same number of times. But they're not accounting for different things. Like every swing isn't the same. They're not accounting for things like wind speed. They're not accounting for things like what if somebody hit one from the top of a hill versus somebody who hit one from flat land? Um, I've gone to Top Golf. If I'm on the third level, I do much better than if I'm on the first level. And my swing is terrible. So just think about where bias could come in to the statistic and also where they might not have sampled enough times to have an accurate picture of the actual population of the experiment. Another thing that leads to misuse of statistics or misinterpretation is when people use vague or ambiguous words. The word average is a very vague and ambiguous word because it has different meanings and there are different averages used in the study of statistics. In a later section, we'll actually discuss these different types of averages, and each one is calculated differently. So an example might be if one source says that the average salary for this one job position is $50,000, but the union for that same job says that the average salary is $42,000. That, who's lying? Who's telling the truth? What's the real average? Well, they might be calculating different types of averages. And so they might actually be telling the truth, both sources, but they might use the average that best suits what information they want to be presenting to the people. So keep your eye out for vague words like average, largest. Largest can mean largest average, largest total, largest building, like largest sales, largest profit, largest loss. You don't know what they're talking about when they say the word largest, so you have to read really carefully into it. Another deceptive technique that gets used is providing statistics that may produce incorrect or irrelevant conclusions. An example might be a paper towel company might say, our paper towels are heavier and so they absorb more. But does weight actually correspond with absorbency? You could potentially have a very lightweight paper towel that absorbs everything, and another paper towel that's heavier that actually lacks absorbency. Um, the example that they say in the book straight up says that a rock is heavier than a sponge, so is that more absorbent? Um, my cat is more absorbent than a paper towel, so should I wipe up my messes with my cats? Like, that doesn't make sense. And so be on the lookout for in like coming to incorrect conclusions based on the statistics provided for you. Another thing to look out for on statistics that might be misleading or lead you to misinterpret information is when you are provided a graph with an inaccurate scale. They might create a scale that might show you a steeper slope because they skip to a higher value and do the little squiggle line at the bottom to show you that they're actually starting at 1,000 and they're not starting at 0. And then their scale might go up by a smaller amount to make the increases look greater. Um, there's an excellent picture of that happening in the example on page 729. Also, scales can be misleading in general. You want to make sure that you are dealing with a consistent scale on a graph. If the y-axis is going up by 5 and then all of a sudden jumps up by 50, that's not an accurate and consistent scale. Now, we hope that that doesn't happen, but there are examples. You could look up like misleading graphs in newspapers, and you would see a lot of pictures of these types of situations. So now let's look at these examples and answer questions regarding misuses of statistics. So we're going to look at this. We're going to say, in a study of patients with cold symptoms, each patient was found to have improved symptoms after taking honey. Therefore, honey cures the common cold. Okay, there could be so many different things. So was the experiment consistent? Were the people who had cold symptoms only taking honey, or were they also taking cold medicine? Were they also taking cool baths to lower their fevers, or taking anti-congestion medicine to prevent their nose from running? Or are they taking sleeping medicine like Tylenol PM or anything like that? So we can't claim that honey cured the common cold based on this study. It also doesn't tell us how many people were studied. It doesn't tell you how many people were surveyed. So they also didn't say how it's improved. Each patient was found to have improved symptoms after taking honey. What does that mean? Did they calculate the number of times they blew their nose and it decreased? Or was it just they felt like they felt better? And were they measuring their fever and saw the fever go down? So there's a lot of information that's missing in this that we cannot conclude that honey cures the common cold. Number 5 says at Central High School, half the students are below average in mathematics. Therefore, the school should receive more federal aid to raise student scores. So we see one of those buzzwords, average. That should kind of put some warning bells going off in your head. What average? The state average? The country average? The county average? Like the average of local schools in the neighborhood or in the city? It doesn't say what average they're talking about. It doesn't say what population they're talking about. Um, they're missing information. They could be talking about the median versus the mean. We don't know. And so therefore we can't make these conclusions. We have to have all the information. So this one is missing a lot of information about, also, is it their grade in their class? Is it their score on a standardized test? It doesn't clearly state what the standard is or what the average in mathematics is actually referring to. So there's a lot of missing information in this example, which could lead us to make decisions about things that might not be accurate. Maybe they're below the national average, but they might be above the state average. Or maybe they're below the state average, but they're higher than every other school in their city. So it's kind of like it's all relative and we need to have all the information. Also, how is the average calculated? We're going to have four different types of averages that we're going to look at. So we need to know how the average is calculated. All right, next one. 80% of all automobile accidents occur within 10 miles of the driver's home. Therefore, it's safer to take long trips. So they give us a value. 80% of all automobile accidents occur within 10 miles of the driver's home. So, but then they're making an inappropriate conclusion from that. They're saying, therefore, it's safer to take longer trips. Well, why would 80% of all automobile accidents occur within 10 miles of a person's home? Perhaps that person only drives within 10 miles of their house on a daily basis and very, very rarely goes past 10 miles. So if you don't ever go past 10 miles beyond your house, you might never have an accident that occurs beyond 10 miles past your house. So that's not necessarily enough information to make this conclusion. This statistic is asking us to come up with an inaccurate conclusion. That's been happening with all of these. We're being asked to make inaccurate conclusions based on missing information within our statistics. I'm going to skip ahead. Number 8 is a quick one. The average depth of the pond is only 1 foot, so it's safe to go wading. Well, again, how do they calculate the average? So what if, let's think of some numbers that would give us an average of 3 feet. An ambiguous word there, but we can also come up with values that would give us an average of 3 feet. So let's say at one part in the pond, like the deepest part in the middle, or maybe there's like a dip that goes in, it's 11 feet deep. And then in 4 other locations, it's only 1 foot deep. So then when I add that up, 11 plus 1 plus 1 plus 1 plus 1 is 15. 15 divided by the 5 occurrences equals 3. So the average depth of that lake is 3 feet. But if I go wading and I wade into an 11-foot deep spot, I can't go wading. So we don't have enough information. We don't know how the average was calculated. We don't know how many samples they had or how many places that they measured. Or samples would have been the spots in the pond in which they measured. So we don't have enough information to make that conclusion. Then we have this table that says the following table shows the average price of a movie ticket in the United States for the years 2009 to 2013. Draw a line graph that makes the increase in average price of a movie ticket for the year shown appear to be small and then appear to be large. So I'm going to draw some quick sketches to match this. I'm going to ask that you pause and try and make your own, and then we'll compare. When I make this graph, and I'll call it ticket price, if I have a scale, so we have each of the years on the bottom, and I have a scale going from 0 to 8, I mean, technically it would go to 9, and I were to plot all of those values, well, the first one is 750 at 2009, so that's about here, and then 289 or 789 for 2010, and then they're all getting a little bit bigger until we get to 2013, which is at 8.13, $8.13. So these stay pretty consistent. Okay. If I have this scale, it looks like there's no change at all. But if I were to make my scale very different, I end up with a significantly different graph. So this one I skipped on my scale with that little line break that shows that I'm making a big jump. I start at 750 and I go up by 10 cents for each one, which makes it look like the jump from 2009, which was $7.50 a ticket, to 2010, which jumps up to $7.89 per ticket, is a huge jump. So the scale matters on these graphs, and it can be used to manipulate the information. If I want to show that there's essentially no change in ticket prices at all, I might use that small scale where the scale that makes a small change. But if I want it to look like they're going up extremely high in prices, I might use a scale like this one. And so you have to be critical and look at the scale on your graphs to determine whether or not it's portraying accurate information. And let's look at this one right here. We have a graph of favorite foods of students at my school. We have hot dogs, tacos, chicken, other hamburgers, and pizza. It shows us the percentage. Let's first look at the scale. And this is just a regular old bar graph. Our scale goes from 0 to 4, 6, 8, 10, and then it jumps up to 15, 20, 25, 30, 35. So what that means is that from hot dogs to essentially tacos, it's showing a shorter jump in between this on the scale. So this is a misleading graph because what's the difference between hot dogs and tacos? Well, if this is about 3%, and this right here is about, let's say, 9%, that's a difference of 6%. Okay, but if I go look up here between hamburgers and pizzas, well, this is at 35%, and this one is at 27%, and this right here is a difference of 8%. Why would the 8% difference be smaller than the 6% difference? So yes, this is misleading. Okay, how would I recreate it so that it's not misleading? I would make a consistent scale. I'd either want to make my scale jump up by 5s consistently, or I would want to rewrite it so that my scale jumped up by 2s consistently. If I do by 2s, I'm going to have a big jump between some of these objects, like other and chicken, all the way up to hamburgers. That's a big jump from under 15 to over 25. That's more than a 10% increase. And that is about the same size as the 6% increase was. So you'd want to make sure you fix your scale so that you have a consistent scale to show the appropriate information. Again, we can look at this one here. How is this graph below misleading? Well, we technically have a consistent scale here. It goes from 0 to 150 to 300. But look at the size of the bars. Okay, so this didn't just double in size height-wise like it should have. It also doubled in size width-wise. And so therefore it looks like it's even bigger than it actually is. The difference looks even bigger than the reality. This actually looks like it's probably 4 times bigger because of how much bigger that building it looks. In an appropriate graph for this, that building would just be taller, not wider. So this shouldn't all be there. Hopefully this gives you some insight on how statistics can be used to manipulate information. So you have to be a critical thinker and really evaluate the information that's presented to you. If you have any questions, you're always free to email me and let me know, or hop into Blackboard Collaborate at an assigned time and get help with whatever you need. Thank you.